All right, let's get started. So welcome everyone to another lecture in our ID 5130 parallel scientific computing course. All right, so in the last lecture we looked at a collective communication, an example of a collective communication which was specifically the MPI reduce function, right, which will basically perform a certain operation on the elements, right, essentially elements or values received from several processes and kind of stores this result, right, on one of the process, right, stores this result on a particular process, right, which is basically specified using the destination process argument in the MPI reduce function call, right. All right, so in today's lecture, let us look at some differences between collective communication and point-to-point communication, such as MPI send and receive, and also we will look at a few more examples of collective communication. Okay, a few more applications. All right, so let me kind of repeat the function prototype for MPI reduce. So that was, if you recall, it was int, return type was int, and then MPI reduce. Okay, so and then the first argument was the input data, so that was a pointer to input data pointer, right. So we have input data pointer. Essentially I would like to explain some of the differences, so for that we may it will be kind of helpful if we kind of recollect what were the arguments. So, and then we have the output data pointer, right, into which essentially the reduced value will be stored, and this is what the elements will be taken from, right. And then we have how many of the elements will be sent from each process, that was basically count, and then what would be the data type of these elements, which will of course have MPI data type as the function type, as the argument type, and then we have data type that we pass, which is MPI int, MPI char, and things like that, and then you have the operator, which also should belong to MPI operator type, so that is basically the operator. And then of course you have to specify on which process you want all this the final value to be made available, so that is basically given by the destination process, right. And you have finally the communicator, so that is basically MPI communicator, and then let's say if you use the lower communicator as the variable. Okay, so in this basically this is the argument that is going in, and this is basically the output that is coming in, and rest of the arguments are all inputs to the function call, right. Okay, all right, so let us see the differences between the collective and the point-to-point communication. So differences between collective and point-to-point communications. Okay, so essentially there are several differences in which the collective communications differ, right, or between collective and point-to-point communications. So we will look at each of them one by one. So the first one is all the processes in the communicator must call the same collective function. Okay, so essentially all the processes in the communicator, of course, must call the same collective function, right. Right, that means what this basically means is that if you write a program which will try to, on a particular process 0, you may use MPI reduce, right, and you may try to match this on, let's say, process 1 using, let's say, MPI receive or something like this. So such kind of things would lead to kind of such kind of things are not allowed, and then they lead to probably program kind of crashing, or kind of it may hang, and it's kind of not legal. It's not allowed to do like this. Fine. So you always use MPI reduce on all the processes, so that it is kind of works perfectly fine. Okay. And then the arguments to the MPI reduce must be compatible. Okay. So essentially the arguments used in collective communication functions must be compatible. Okay, what do we mean by compatible? Essentially, if you are calling, let's say you go back to the function. Let's say if you call on process 0, you specify the destination process to be 0, and then on another process 2, you specify the destination process to be 2. Okay, so this is not allowed, because it should be all the process should specify the same value. Okay, same process as the destination process. Okay, so similarly all other arguments must also be compatible. For example, the data type should be the same on all of them, operator and all these things. If it is not, then essentially MPI reduce may kind of give a erroneous result, or it may even the program may likely to hang or crash. So if they are not compatible, then an erroneous result may be produced, or the program may hang. Okay, so you should kind of avoid such circumstances. All right. So another one is that if you carefully look at the collective communication MPI reduce here, you see that essentially your input data P should be provided by all the processes, right? They should be provided by all the processes. Then you may think, okay, the output data P is actually really not required on all the process. It's actually only required on the destination process, right? And on other process, this is this required, right? So that might be the question, and you may be tempted to pass just a null on other process, but that is kind of not allowed. Okay, so what you have to do is you still have to have a pointer, and that pointer essentially you still have to have an argument, real argument, and that argument can be a pointer like here, but then that pointer may just point to a null, okay, instead of to a proper memory location on all other process other than the destination process. Fine. So the third difference is basically, or essentially the if not the difference, the features or the correct way of using collective communication is that the output data pointer okay, argument is only used on the destination process, but okay, however, all the processes still need to kind of supply an actual argument corresponding to output data pointer. Okay, so essentially, however, all the processes must supply an actual argument for output data pointer. Now, although this could be, even if it is kind of just a null, okay, it might be just point to a null value on all other process, okay, but still you need to supply that. So that means you cannot just write null there or any other number there. Okay, so then one of the most important differences is basically between collective communication and point to communication is that the point to point communications are matched, as we have already learned, based on communicator and tags, right? Whereas the collective communications essentially do not have tags. So the collective communications are matched solely on the basis of the communicator and the order in which they are called. Now this is something we need to take a look at, in which they are called. Okay, so to understand this, let me kind of use an example of let's say MPI reduce called 2 times on every process, and I'm going to kind of list down here how MPI reduce is used. So let us take a look at an example, because we would like to kind of understand how does this communicator and the order in which are used to basically calculate the values. Okay, so basically we are looking at an example in which we are calling MPI reduce is called multiple times. Let's say we are calling 2 times. Let's say on process 0. Okay, the code is something like this. Basically you have you're initializing a equals 1, let's say b equals 0, c equals 2, d equals 0. Okay, so this is what I'm initializing for all the 4 values, and then we specify the destination process to be process 0. So destination process is equal to 0. So if I call MPI reduce on process 0 2 times, so I call MPI reduce, and then I pass in the input data as ampersand a and the output data is ampersand b. Of course I have all of these things, and the destination process and the communicator. And then in the next line I have another call to MPI reduce, in which I'm going to call ampersand c, ampersand d, and then of course the destination process is 0. Okay, so that's what we have. And then on process 1 we initialize values to be the same. So a equals 1, b equals 0, c equals 2, d equals 0. Okay, so we have 1 0 2 0. Then we again call MPI reduce. Okay, and then we would call here, instead of AB I would place the ampersand c, ampersand d first, and then 0. Oops. And then the call to AB would be made the second one. So you have ampersand a, ampersand b, 0, like this. Okay, fine. And then on process 2, so this is the final process on which again we have a equals 1, b equals 0, c equals 2, d equals 0. Okay, and then we have 2 function calls, and then these are the same as what we had on process 0. So this means you have ampersand a, ampersand b going first, then followed by ampersand followed by c and d. So we have MPI reduce, right, ampersand c, ampersand d, 0, like this. Okay, so so I mean, okay, when you write the code you would not write it this way, because you would just call one MPI reduce and that will be seen by all the process. But say for example you have written a process specific code like this, in which you can swap only for process 1 you would like to call MPI reduce ampersand cd first, then ampersand ab, and then on other process you want to call AB first and CD next. Okay, so that's what it is for an example of 3 process, right, 0 1 2. Now if you take a quick look, you may think that the values obtained by A and B or B and D will be, let us say you might think or we might guess that AB is called here, so so A has a, so A is the input argument here, and then input argument here, and then input argument here, right, and then B is the output argument here, here, and here. So as a result we might say that okay, B would get a value of sum of all these things, so we get A, so that will be B would get a value of 3, and then we say okay, C would get a value of C will be the input, C will be the input, and then C will be the input, and then the output here would be D, D, and then D. So basically all 3 D's will have C as the input, so D will get a value of C has a value of 2 on every process, so this basically 2 plus 2 plus 2, this would be 6. Okay, so we might think this would be the value that B and D will have after the function call on the destination process, that is basically 0. But that is not correct, because when you call a collective communication, it is, as we said, it doesn't have tags, it doesn't work with tags, so it is solely based on the communicator, which of course we have provided it to be the same on everything plus the order in which they are called. Okay, so the order in which they are called is important here, and we also realize that except for the destination process, that is 0, the output data P is actually irrelevant. That means the first function call will be this one, and this one. So that will be first worked out before it goes to the second function call. And on process 0, the output data P is this one, right? So this is your output data pointer, okay, which is B. So the final value stored in B on process 0 will be %B. So it really doesn't matter what argument is provided here on the other process. So that means this is irrelevant and this is irrelevant. Only thing that is relevant is the A here, C here, and A here. So as a result, the value stored in B, right, on process 0 after the first function call is basically will be equal to sum of the values of A plus C plus A. So that will be A equals 1, C equals 2, this will be 1 plus 2 plus 1, this will be 4. Okay. Similarly, the second function call is MPI reduced to %C and %D. So value stored on D, that is on destination process, would be equal to value of C plus A plus C. Okay, so that will be C plus A plus C, that will be 2 plus 1 plus 2, so that will be 5. Okay, so the value stored will be, instead of 3 and 6, the value stored in B and D will be 4 and 5. Okay, so that is how collective communication works. So the order of the collective communication is important, and then the name, okay, essentially the name of the variable. Okay, so the order of the calls is important, and the names of the variables is irrelevant. Okay, so initially what we thought was, okay, if it will kind of try to match it based on the names, and that is not correct, right? Because it only tries to match it based on the order in which it is called, and then essentially within the same communicator. Okay, fine. So that is as far as the difference is concerned. So we covered how many? 4. Okay, we have one more. So the final one is the final difference between these is basically we may try to call the MPI reduce or any other collective communication with the same input data P and output data P. Okay, that means, let's say if you want to call MPI reduce, you may say, oh, I don't need this value anymore, so shall I call it with %x, and so on, destination process 0, and the communicator. Now this kind of call is kind of illegal in MPI, because this is basically known as aliasing in the context of programming, and aliasing is actually unfortunately not allowed in Fortran. Okay, aliasing the output variables, although it is allowed in C. So as a result, MPI kind of, which would like to keep similar structure for both C and Fortran, okay, it doesn't allow for aliasing. So as a result, such kind of thing is illegal, and if you use, now what will happen? Essentially, if you are lucky, you may get a result. So it may produce correct result if you are lucky, or it may produce incorrect result, or the program may even hang or crash. Okay, so essentially the output is unpredictable. So as a result, you should kind of always avoid such kind of things in your code. Okay, so you don't want to introduce a element of unpredictability into your code. So such things are not allowed. Fine. Okay, so these are essentially the main differences or similarities when it comes to the collective communications. All right, so basically we learned about one collective communication, that is MPI reduce. Now let's say in the trapezoidal rule, it was all right to basically calculate the different integrations and then kind of sum them together on process 0, right? So essentially it kind of received the elemental values and we sum them here. However, you can think of another situation. For example, let's say in your Jacobi or in the Gauss-Seidel method, right, we have learnt about the stopping criteria, right, or the convergence criteria, right, which basically checks for some kind of a norm, right, checks for some kind of a norm, and then if that norm, let's say between the solution vector at x plus k plus 1 and x plus x of k, let's say it's some 1 to infinity, some norm here, right, if this is less than or equal to some epsilon, some tolerance we specify, then we want the program to stop, right, so we want the program to stop, right. So this is one way. The other way is, of course, we looked at the residual, right, calculate residual b minus axk, and then if this residual is less than some value, we would like to stop it, right. So these basically ask for the value of this x tilde k plus 1 minus x tilde k to be available not only on process 0, because this value should be available on all the processes, right, for every iteration, right, these should be available on all the processes for every iteration. So it is kind of not very efficient if process 0 collects it and sends back to process 1 and so on. So that means we would need to have this kind of value computed on all the processes, right. So this kind of context is different from what we have learned in the context of MPI reduce. Okay, so when you have this situation, then obviously one thing we can think of is basically having a similar to the MPI reduce, we may have a tree-like communicator or tree structure communication, right, in which the value computed would be again sent back in a reverse way. For example, let's say if you have 1, 2, 3, 4, 5, 6, 7, 8, then MPI reduce would basically work this way, right, as we learned. So every other process would send it here, 0, 1, 2, 3, 4, 5, 6, 7. Then in the next function call, we have only the even number of processes 0, 2, 4, 6 to work with, and 2 would send it to 0, and then 6 would send it to 4, and eventually 4 would send the values to 0, right. Okay, this is so nice. Okay, so it sends here. Now whatever this value is here, now we can reverse the tree here. So we can say now 0 will send it back to 4, right, and then now 4 would again send it back to 6, right. So 4 would continue to 6, and then 0 would basically send it to 2, right. So I can draw a little longer here, and you have 2, and then essentially 0 would send it to again 1, and then 2 would send it to 3, 4 would send it to 5, and then 6 would send it to 7, right. So you have 0, 1, 2, 3, 4, 5, 6, 7. Okay, so that means we basically okay, the last circles look really rough. All right, so basically we have kind of mirrored this communication, right. So we kind of either reversed or mirrored the communication to send back the value to all the process. So we can probably adapt something like this, or we could think of a situation in which instead of a one-way communication like this, we can have probably an exchange of data, right, by pairing up the processes, okay, which is sometimes referred to as a butterfly communication, which kind of looks like this. Okay, essentially you have your let's say again we have 8 process, 0, 1, 2, 3, 4, 5, 6, 7. Okay, and then let me draw a few more. Okay, so we have these, then okay, so this is I'm now drawing the 4th layer. Okay, so then instead of the even process, the odd process sending it to the even and so on, like what we saw here, we'll basically have an exchange of data. That means 0 and 1 exchange their data, and then as soon as they receive, they are going to sum it up. For example, 0 has some value of 2 and 3, and then 3 as soon as it is on this, so it will make it 5 and then 5. Okay. So similarly, 2 and 3 would exchange in the first step, and 4 and 5 would exchange, and 6 and 7 would exchange. Okay. Now after this, all of them has the same value for this pair of process. Now these two pair would basically now exchange with the 2 and 3, and the 2 and 3 would exchange with 0 and 1, and similarly 4 and 5 would exchange with 6 and 7, and 6 and 7 would exchange with 4 and 5. Okay. So after this step, then again you have a partial sum that is kind of the same on all these 4 processes, and another partial sum that is same on all these 4 processes. Then finally your 0 would send it to 4, right? So 0 would send it to 4, 1 would send it to 5, 2 would send it to 6, and 3 would send it to 7, right? Similarly, and this guy would send here, and here, and here, and here. Okay, so this is not nice, but you probably got the idea. So this kind of a communication is known as the butterfly structure communication. Okay. So this is also is possible, and of course you can think of few other ways of doing this thing. So again, we don't want to get into a situation of which is the optimum way of sending, of doing this. So in order, depending on the number of processes we are working with, and the topology, and the the architecture of the machines or whatever, so we don't want to think about what is the optimum way of doing this thing depending on the size of the values you are passing and things like that. So as a result, MPI kind of provides an optimum function call, just like it has done it for MPI reduce, and that is known as MPI all reduce. So it's called MPI all reduce. Now all reduce is single word, and A should be capital, just like to be with the correct format of the the MPI. So then let us see this function call. So this would be very similar to what we had for reduce, except for one argument missing, and that argument, as you can easily guess, would be the destination process, because now the destination process need not be specified because it will be available on all the processes. So you have MPI all reduce, you have void star input data pointer, and you have void star output data pointer, and then you have count, right? So how many values are being sent from each process, and then you have the MPI data type, and that is your data type, and then you have the MPI operator, that is the reduction operator you would like to do, which is either sum, multiplication, or the logical AND or whatever. And then you have finally the MPI communicator, which is basically, earlier you had the in between you had the destination process, which was int type, and now you don't have it. So only difference is that no destination process needs to be specified, and that is understood because the value will be available on all the processes. Okay, fine. So now up till now we have been only discussing about how to essentially the output, right? Essentially, can we print the global sum from process 0, or can we make something like a convergence criteria, right, to be available on all the process, so this P0, P1 all the way to Pn-1. That's what we have been thinking. Now if we could do all these things using MPI reduce and MPI all reduce for the output, we should be able to do something similar for the input as well, right? That means if you were to, let us say we want to read some values, and then we want to basically supply these values that we have read on process 0 to all the processes, right? Now that is something, of course, we can do using a similar tree-like structure, and of course MPI provides a function call for it, and it is known as MPI broadcast. Okay, so that is known as the broadcast function call in MPI. And again, we could use a tree structure communication, right? So that means what we have to do is, of course, you basically let's say the process 0 reads in some input, reads some input from the user, right? And this needs to be sent to all the process, right? So this needs to be sent to all the process P1 to all the way to Pn minus 1. Now, of course, this can be again done using a tree-like communication, and we can only work with the lower branch, right? Basically, now this is what we are talking about. So you basically have a tree structure, and this is the process 0 can keep sending the values to all the processes, right? So this is like, here it was like the global sum, but now instead of this, if you have read in some value into A, and that A value can be sent by process 0 to 4 initially, and then 4, and then 0 would send it to 2, and 4 would send it to 6, and so on, right? Eventually you will have all the values will have this value A sent by process 0 copied onto all other process. Okay, so the function call, let us take a look at the prototype of the function MPI broadcast, and it has int return type. So you have MPI broadcast. You would need a pointer to the data, so that would be void star data p, and then you would need to specify how many of data p you are sending. So you could be sending 1 integer or 5 reals or 100 double or something like that. Then of course you need to specify the data type that follows. So MPA data type, so this is the data type that you are sending, and then eventually, of course, you need to also say on which process this data is available and which process is basically sending it to all other process. So just like MPA reduce, which had the destination process, here you will have a source process, right? So source process, that means where the data is available, right? Essentially from there it has to be sent to everybody else, and of course you need to specify one final argument that is basically your communicator, right? MPI communicator, this is your communicator. Okay, now in this, if you look at the input output values for this data P is basically acts as both as input as well as output, whereas this is in, everything else is an inlet, is an input, right? Okay. So what does this in out mean for data P? Up till now we either had an input data P or an output data P, but now we are having data P which we say it is both an input and output. So when we say like this in the broadcast, what we mean is that when we say like this, so data P is basically an input on process 0, or it's actually input on source process, right? Because source process would pick up the value, right? And then it is basically an output on all other processes, right, except the source process, because that is where the value will be updated, right, or written. Fine. Now this needs to be somewhat contrasted with your input output on a function call, right? So if you're talking about a serial code or something, or even a function call where you say input output, that means that particular function call for a particular variable, if we say this is both input and output, that means its value will be used and eventually that value will be updated, right? That's what we mean by input output of a particular argument for a function call. Whereas in the context of MPI, specifically in the context of broadcast, when we say a particular variable is both input and output, we say that we mean that that variable is an input on a particular process, which is here is a source process, and then it is an output on all the other processes. Okay, so that is kind of the difference we see in the between input output arguments on a regular program and on the MPI program. Okay, fine. So so far so good. Now we were able to till now basically use this MPI reduce, MPI all reduce and scatter to either collect the output data or to send the input data from one process to all other process. Now it is very easy to think of a situation in which you could be working with not the entire array, right? Rather you will be working with only a partial array. Let us for towards this, and let us take an example of the the addition of two vectors. Let's say we're talking about vector addition, okay, on using MPI, right? Then what, the way you would accomplish probably this would be, let's say you have a vector x tilde which basically has some values x0, x1, all the way to xn minus 1, okay, and then you have y tilde, in the case use braces as well, y tilde will be y0, y1, a simple case would be yn minus 1, okay, simple case would be addition of these vectors, right? And then we would like to add these vectors and store the value in z, right? You basically have x0 plus y0, xn minus 1 plus yn minus 1, okay? So we want to perform this operation, and let's say n is equal to some very large value, let's say 10 power 6 or something. Then how would you do in MPI? Well, of course, first of all, you need to read x tilde and y tilde. Let's say we read this from user, okay, through a particular file or something like that. Of course, if you don't want to key it in, it will be too many if you key it in. So you can read it from a file or something on process 0. Okay, so on process 0, x tilde and y tilde are available, and the entire array which contains, let's say, 10 power 6 elements, so that is 2 into 10 power 6 elements. Or let's reduce the number so that it will be easy to work with. Let's say n equals 1000. Okay, but this can be considered to be large enough so that we don't want to duplicate the values. Okay, that means, and then we have 2000 values of x tilde and y tilde stored on process 0, right? Now, how does we want to work with? In MPI, you would like to kind of partition this into multiple processes, and then we would assign this x and this x to one process, and then we would assign x and some bunch of values to another process, and then the remaining ones to another process, and so on, right? So it doesn't make sense, it does not make sense to allocate the entire 1000 elements on every process, right? So it doesn't interest us to allocate all 1000 elements on all process, because anyway every process is only going to work with a chunk of the array, right? So each process is only going to work with a part of the array, right, or a chunk of the array, right? So as a result, it doesn't make sense to allocate it everywhere, but we would like to write a function which will basically send out, let us say if there are n procs, the number of processes, then we would like to have a function which will send out n by n procs to each process, right? The first n by n procs to one first 0 will be left in the 0th process, and the next one will be sent to process 1, and the next one to process 2, and then all the way this one to process n procs minus 1. Okay, that's what we would like to have. And if we do it that, we of course, again, we don't have to do it this manually. We have a function in MPI that MPI provides, which is called scatter, which does this job. Okay, so the function call in the prototype goes like this. So basically we have int MPI scatter, okay, and then this is going to scatter the value. So we have void star send buffer pointer. Okay, that means what is the send buffer that we are going to, the pointer to the memory here, and then how many are sending int send count, and then of course you have to specify the data type, that is MPI data type would be the this is the send type. Okay, so that is about the sending buffer, and then we should have 3 more arguments, as you guessed, for the receive. So that will be void star receive buffer p, and then int would be receive count, and then MPI data type would be the receive type, And then of course we also need to specify who is sending it. So we need to specify the process who is sending it. So int source process would be sending it, and then you would of course need a communicator. So that is basically MPI communicator. Okay, so that means so that's basically the send buffer, which would basically contain all the 1000 elements, would split it to, let's say if you have 10 processes, it will send into 100 elements each on every process. Okay, so as a result we are not duplicating it, and every process would only get whatever it is the amount of array that it has to work with. Okay, now this send count here is important. Okay, this send count and receive count here, and then the send count is basically tells you the amount of data that is being going or sent to each process. That means the send count would be 100. Okay, it is not the size of send buffer p. Okay, because the size of send buffer b would be 1000. Okay, so that needs to be kept in mind, and of course receive count would also be 100. And it is also important that you match the data type that of what your the send type would with the receive type. Okay, so you make sure that you match these types so that there are no errors. Okay, so that is about how we could use the MPI function called MPI scatter to send out to kind of distribute the amount of data that we have among the processes, such that they can work with whatever is the data that is available to them, or that is what is required by them. Okay, now of course we could do kind of a reverse operation of this thing. You can think of it something like this. For example, let's say you have a function in which you need to have this final addition, right, final value of the z vector, which is basically z0 all the way to zn minus 1. Now as of now we only have it kind of in chunks, right, because this is only available on p0, this is available on p1, and this is available on p n prox minus 1. But then you may want to again get this data from all the process onto process 0, so that process 0 probably would again write to a file or would print it to a screen or something like that, right? Basically we would like to now do a reverse operation of what we have done in scatter, that is basically collecting all this information and then putting it on 0. Again you would see that the amount that is, the amount of data that is collected from each process would be only 100 elements, say for example, and then the process 0 should basically have 1000 elements of memory allocated, so that it can collect the 0th chunk into the 0th block here, first chunk from process 1 into the chunk from process 1 into the first block here, and so on, and the last and the chunk from process n minus 1 into or n prox minus 1 into the last block here on process 0. Now that can be achieved using the reverse operation can be achieved using the function known as gather, okay, which basically gathers all the individual blocks from every process, and then it will put it into the respective blocks. Okay, so that will be matched. So 0, 1, 2, this rank of the process will be matched in the way it is putting it onto the process 0. Okay, and now let us see how does the function call look like. So you have int MPI gather, and then you have the void star you basically have the send buffer pointer, right, and then similar to the previous one you basically have int send count, right, and of course you need to have the data type. So this is basically MPI data type, this is again the send type, and then you have the 3 arguments, which is basically void star receive buffer pointer, and then int receive count, and then you have the data type, this is basically the receive type. Okay, and then you have instead of the source process you have now the destination process that you would specify, and then finally you basically have the MPI communicator, right? Okay, now What about the receive count here? I think we need to just pay attention. What is the receive count here? Okay, so receive count is basically the number of data items that is received from each process. Okay, so this is basically 100. Okay, so this is receive count is the number of data elements, right, received from each process. Okay, not the total amount of data that is being received. Okay, so this is only 100. Okay, of course send count is also 100. Okay, but this is basically what is being sent from every process. So if I were to kind of draw a schematic, so basically you have, let's say, some chunk of array, let's say some 4 chunks which are all equal and supposed to be equal in size, which are all being sent to process 0. Okay, so basically process 0 has this, process 1, process 2, process 3, and the destination process we specify as 0. Then all of these guys would send the values to process 0, right? So basically process 0 has some values, process 1 has something, process 2 has something, and then process 3 has something here. Okay, so all of them will send the values, and then we're going to basically get on process 0 the values from the first block, and then the values from the second block, right, and the values from the, I hope I have used this one, okay, third block, and then the values from the fourth block. Okay, so that is how your values will look like on process 0, right, after the call to MPI gather. Okay, so these are the send buffer pointers. And then of course you need to allocate much longer receive buffer memory, because it has to allocate now n procs times the send count that is being sent by every process. Okay, so these are all individual ones, have 100 elements, let's say, and then we have 1000 elements memory needs to be allocated here. Okay, so that is about MPI gather. Alright, so with this I'm going to kind of stop here, and then we can we'll continue from here in the next lecture. Okay, thank you, talk to you in the next lecture.